Well, welcome everybody to our Making Better Designs and Decisions. We're going to be talking about FEA and CFD today. The speakers are Mike Spence and Andrew Gross from Dassault Systems, the guys that put out SolidWorks. And without further ado, I'll just let them get right into the presentation. Thank you.
Cool. Thanks, Lars.
Oh, sorry.
Yeah.
There is a dory. If you guys have any questions, just type into the dory and I will be sure to ask Mike or Andrew your questions. Thank you.
All right. Well, thanks everybody for joining. My name is Andrew Gross. Yes, like Lars said, we have Mike Spence here also, my colleague. And we work on the SolidWorks side at Dassault Systems. And today we're going to talk a little bit about, we like to say making better design decisions, but by and large, we're going to talk about simulation, and simulation being our FEA product, which is called SolidWorks Simulation, as well as our flow simulation product, which is a CFD tool. So when SolidWorks started, we used to use this analogy all the time. SolidWorks is like a pocket knife or a Swiss Army knife. It's got a blade, it's got a can opener, it has a wine bottle opener. But as we've really kind of evolved, it's actually, we think it's less of a Swiss Army knife, more like a massive toolbox. There are just so many things that you at Google actually have access to, as well as things that we make, products that we make. And as you can see, our product line is pretty vast. So we're not going to spend time talking about our entire line of products. We're really going to be we're going to focus on the validation side. But you guys probably know about our mechanical design family of products, which includes SolidWorks and some of our other 3D Experience platform products. But we also have an entire electrical set of products for electrical design, creating schematics, as well as PCB design. You guys, I believe, use our PDM product, SolidWorks PDM, which is a data management tool. We have a lot of collaboration tools which help for people to create product documentation, which is called Composer, and visualize, as well as creating inspection documents and model-based definition tools. So it's pretty vast. We are really going to focus, like I said, on our validation tools. So our simulation tool, which is FEA, and our flow simulation tool, which is CFD. Within this line of products, there's also our plastic injection molding simulation product called SolidWorks Plastics. We're not going to talk about that today, but you guys actually do have access to that software here as well. You guys really have kind of the full suite, or close to the full suite, of SolidWorks products. So I'm going to kind of take the first little section here. Mike Spence will come and take the second later. I'm going to talk about our CFD product, which is called SolidWorks Flow Simulation. And looking at the screen here, I'm not sure if the column all the way on the left, if it's completely washed out, or if you guys can actually read the words on that, because here, actually on this projector, we cannot read those. But our flow simulation product is a tool that's designed to help understand how fluid flow, both thermal fluid flow, or if you're not interested in the thermal aspects, but fluid flow around parts and assemblies that we design. So we're looking at either laminar or turbulent fluid flow. We can do heat transfer problems. Heat transfer could be like, say, from one fluid to another, or from solid material to the fluid and back. We can even do things like understand rotating regions, where you can simulate a fan moving in the fluid space, or a pump. We can see non-Newtonian fluids, and even run time-dependent transient studies. And we also have a couple other packages that add on to our flow simulation package, one called Electronics Cooling Module, the other one HVAC. They're pretty specific. Here at Google, I would think that the Electronics Cooling package probably would make a little bit more sense. This is where we actually extend the abilities of SolidWorks Flow Simulation, so we can understand things like joule heating. You can have a dedicated simulation on for understanding two resistor components, which basically is a simplified version of how a microchip heats up and how it heats up a circuit board. And I'll show you a little bit more about that later today. All right, so I'm just going to cut right into the presentation at this point. So thanks, guys. Sorry, that took a little longer than I wanted to get through that. So this is an image that I found while doing some research. So this is actually a part of an exhibit in the Chicago Museum of Science and Industry. And what these are actually, these were used in a court case from Thomas Edison when he sued a bunch of patent infringers. If we know anything about Thomas Edison, yes, he was the Wizard of Menlo Park, but he also was a pretty savvy business guy and definitely did not like people infringing on his patents. So an interesting part of this photograph, all of these light bulbs were all developed. These were all pretty much prototypes, but these are from 1893. And I'm not sure about how clear the video is for those of you who are watching from behind your desks. But if you look at the socket, that's called the E27 socket. In fact, these bulbs, if you could break the glass in this exhibit, you could probably go home and fit these into your light fixtures at home or into your ceiling fixtures at home. And if the bulbs were working, well, they would actually turn on. So the light bulbs that we see even today, they really are the same form factor, even the same interface that some of the first bulbs the first commercially made bulbs really had that exact same interface. So I'm not sure when the last time you guys went to Home Depot, but you probably don't see a lot of incandescent bulbs anymore. They all kind of look the same. They all kind of look like this floodlight, but if you know nowadays, they're all LEDs. So we're taking things like an LED driver, a heat sink, an LED array, and you're really trying to jam that into a 125-year-old form factor. So really what I'm trying to highlight is that this is a pretty challenging, engineering problem, right? There's a lot of activity in the market of people creating LED light bulbs, right? They can run at about 10% of the wattage as an incandescent bulb, but they really have to keep that exact same form factor, exact same interface. So this is a pretty challenging engineering challenge, which I'm sure you guys run across daily. So what are some of the challenges we would see here? Well, if we were tasked to create an LED bulb that had to basically take on a 125-year-old form factor. Well, you may want to understand, is everything going to fit inside the form factor? Obviously, that's going to be problem number one. Well, next, is it manufacturable? Well, you might be able to get everything to fit, but if it costs $500 to make each light bulb, it's probably not a very viable solution. So that brings us to whether it's cost effective, right? These light bulbs go for like 15 bucks. Well, can you make one for $1? That's really, so SolidWorks can usually help with a lot of these problems. What about whether or not it'll overheat? As we know from LEDs, they really need to stay at a very kind of like a really narrow temperature zone for them to be efficient and to not burn out quickly, right? Most of these bulbs say they last for 50,000, 40,000 hours, right? You can get 25 or 30 years out of these bulbs, but that's only if they don't overheat. If they don't overheat, you just can slash those numbers in half or in quarters. So SolidWorks can help us with a lot of these problems. Will everything fit? Is it manufacturer? Obviously, SolidWorks can help us with all of these things. Is it cost effective? Are we using an appropriate material? We can even use things like SolidWorks costing to help understand how much it would cost to manufacture it. But what about the question of whether or not it'll overheat? Does SolidWorks out of the box can really help us with that problem? And this would be a standard problem that you would use something like SolidWorks Flow Simulation to help answer. SolidWorks Flow Simulation also can help us out with some of these other questions, like whether or not it's manufacturable, right? What if we're building a heat sink? Well, it's going to help us understand if that heat sink is effective enough, and if that heat sink, how expensive is it going to be to manufacture that heat sink, or if it's cost effective. We might even be able to determine that a less expensive material could be used that functionally is exactly the same as maybe a more expensive material like copper. Maybe you can substitute aluminum for copper. So in this LED retrofit bulb project, we've really narrowed the scope, and we're going to be using this Cree ML-B lamp. This is the actual light source, and we know that it runs at a 0.5 watt. And based on the material data sheet from this product, we can see that that when you get too hot, solder points. It reduces the lifespan and the optical characteristics of that LED. So it's really critical that in your design that it does not get too hot, right? So that's one thing that we're really, like, when you're designing a form factor like this and you understand the environment, we know that specifically with LEDs, they need to stay within a very specific temperature range for them to hit their 50,000 hours and to make sure that the color temperature is accurate. So a question you might have when you're building this model is, well, how many fins would be best for that heat sink, right? Obviously, or we may think, obviously the more fins, the better for cooling, but the more fins also might be more expensive to manufacture. So really what you want to do is develop a heat sink in this type of application that has the least number of fins, of heat sink fins, least amount of material, but also can effectively cool those LED chips while in service. So at this point, I'm just going to kind of jump right into SolidWorks and show you kind of how you would start to answer a question like that if you already have a simple model. So in this case, you can see I have a version of an LED bulb. If I zoom in, we can see that each of these LED chips, this is that Cree ML-B chip, which is mounted to a simple circuit board. If I slice it in half, you'll see that this is a simplified model. In this case, I may not be at the point where I'm adding wires. I may not really add a lot of some of the guts of the bulb. I may just want to, understand what's the performance of the heat sink in relation to a hot circuit board that's being heated by these half-watt chips, as you can see on the bottom. So I'll show you how I'll start using SolidWorks Flow Simulation to start building a very simple analysis that should be able to give us really quick feedback to help us understand the performance of this bulb. So I'm going to further simplify our model. You can see that our ML-B LED chip, in this case it has, there's a few different parts here, obviously. It's not super complicated, but it's a somewhat complicated chip. It's really nice that Flow Simulation, we can even further simplify that model. You can see that in this case, what we're going to be analyzing here is just simply a block. And we're going to use something called a 2-resistor component model to help us understand a very realistic environment of the heat environment of this chip without needing all of the overhead of a very complicated piece of geometry. All right, so for this model, I've just simply hidden the, you can see it's there. The body is still there, but I've hidden it for this, to start the simulation just to help us kind of visualize what's going on. In fact, I'll go ahead and unhide it for now. So starting Flow Simulation, it's really pretty simple. You always want to start with a wizard. The wizard is a very easy way for us to set up some initial conditions, the initial physics of our model before we start adding things like boundary conditions. So one of the first things we do always is we want to name our project, right? So we'll call this, Google Test LED Lamp. And the next window, again, most of these windows are just designed for convenience. So this is where we would choose our operating or our unit system, right? We may be collaborating with folks overseas. In the United States, we tend to use, inches, pounds, feet. If you may be interfacing with folks in Asia, they may be using millimeters, grams, seconds. Or what if it's a combination of all of these different units? And when you start talking about flow simulation, you start kind of, you get into kind of what could be a veritable rat's nest of units. You start looking at geometrical characteristics, you start looking at loads in motion. There's a ton of different physics and a ton of different units. And one of the nice things we can do here is we can actually create a new unit system that could be like a mixture of whatever you and maybe collaborators use based on whether it's area or volume or even things like acceleration, force, or mass flow rate. It's really pretty convenient. In this case, we're just simply going to use SI units, but it's really a very convenient feature if you have a very specific set of units that you use on a daily basis. All right, so for this flow simulation, we are going to be analyzing this bulb as if it's kind of working in place, right? So it's maybe mounted to the ceiling. We're going to say in this case, maybe it's not blocked by shrouding or any other kind of ceiling fixtures. It's kind of just mounted right into a ceiling fixture. So we know that that's going to be an external analysis. We're going to look at the external air around it as being a fluid, as being just standard air. We also can do things like internal analyses, which that would be really useful if you were doing something like an electronic coolings type application where you had an electronic enclosure and you had specific locations where, say, air entered the model and air exited the models through vents or fans. So that would be an internal type analysis. In this case, we're just simply looking at external. We also want to obviously turn on heat conduction in solids. Sometimes we, our people who use flow simulation may only want to understand aerodynamics, so they don't really care too much about heat. In this case, heat is going to be the most important results. Of course, we need to know that. And we also want to turn on radiation, because sometimes we have very hot things next to things that maybe are not very hot. And radiation can really help us understand the temperature and heating environment that we're in. In this case, the radiation model, we're going to use discrete transfer versus discrete ordinates. Okay, well, what does that mean? We may not understand what those mean, what the difference between discrete transfer radiation versus discrete ordinates radiation model. Well, in every single open dialog in SolidWorks Flow Simulation, we always have a help button. And the help in SolidWorks Flow Simulation really is excellent. So if I had a question about what the difference is between discrete transfer and discrete ordinate, well, I can just kind of scroll through this help, look for radiation. It's going to give me a little bit more information on radiation. And here we have a lot of information about, well, what is discrete transfer and what is discrete ordinates. So anytime you have a question about what a certain property means in flow simulation, the help button works very well, and we have an awesome help environment. Please use it. All right. We also want to turn on gravity, right? This is a natural convection type system. We're not going to have forced air convection. There's no fans. We're not pumping any air or fluid. It's purely natural convection. So we're going to choose, in this case, we'll have gravity pointed straight down as if it were mounted to the ceiling. Now we can also change the gravity location, and that may be another really important result. Maybe you tell your users, well, always mount this light bulb directly into the ceiling. Well, one thing we know about users of our products is they don't necessarily always use them the way we tell them to. Someone may put this flood lamp, may apply it horizontally. But we may want to also test a different temperature environment and make sure that it can last in that type of situation too. So you don't end up with kind of what happened with whatever the Xbox 360, right? When it was oriented in the wrong direction, that's why you got that blue ring of death, or the red ring of death, is just because people mounted it the way it wasn't supposed to be mounted, and it burned the chip up. So these are real world problems. All right, so what type of fluid environment will this bulb be in? Well, it's going to be in air. So we'll choose air. And this is a nice little feature. So instead of picking every single part and choosing a material for it, what we can do in flow simulation is call the entire model one material, and then either import one by one the materials from SolidWorks, how we have them defined, or choose from the engineering library and engineering database in flow simulation and choose those materials. So in this case, because our heat sink's made out of copper, I'm just going to call everything copper right now. And I'll go back and I'll pick and choose some materials later that I'll choose one by one. Okay, so we're pretty much done with the wizard, and you'll see when I hit finish, it's going to start, it's already figured out or solved some of my, didn't solve anything, but it gave me a starting point, which is going to be adding all of those initial conditions. What's the initial temperature, which I kind of went through that screen a little fast, but I was able to choose the initial temperature, initial elevation or pressure. If there was, say, a certain breeze going through my computational domain, I could have assigned that as well in the initial conditions. Okay, so the first thing that we'll see is that our product is in a giant box. So this giant box is our computational domain. This is where we're saying this is filled with air in this case, or it could be filled with water if it's an underwater application. So whichever fluid that we define in our initial conditions, we're going to assume that our computational domain is filled with that fluid. We can also change the computational domain, and you may want to change that size, because obviously the larger the computational domain, the more you're solving. And we may not really need to have this much negative space here. We may want to shrink this up a little bit. So simply by clicking computational domain, I can just really click and drag and shore this thing up. If I want to be more specific about these dimensions, I can actually edit the computational domain and plug in actual real values here. So in this case, I'm going to say that this is fine. We know that most of the activity is going to be taking place below or above our bulb because of gravity and the direction that we've chosen for gravity. So we want to make sure that we give it enough space up top so we can see that entire plume and watch how, like, where heat is generated and where it's going and how hot it is. Okay, so for now, I'm just going to go ahead and I will hide the computational domain and start applying a few more materials. So in this case, I'll add some solid materials. We're going to assume this entire outer casing. We're going to assume that that is some ABS polymer. Pretty common for a lot of LED bulbs is ABS. ABS is pretty good with high temperature. Add a couple more here. So I'm going to go ahead and hide a portion of this just so we can get in a little further. We've already defined our heatsink, but there's also a circuit board and an aluminum spreader plate that we'll need to define material for there. So I'll cut this in half so we can get a little bit better ability to kind of pick on different materials here. So I'm going to find the aluminum spreader plate, which is just part of my PCB here. You can see it's just one of the solid bodies within the PCB part. So I'll choose that solid body, and we'll call this aluminum, 6061 T6 aluminum. All right, and one more material. We also want to define the circuit board. So the circuit board, in this case, we're going to call it just this simple FR4 printed circuit board material. As you can see, we also have non-isotropic materials. So say you have a 6 or 8 layers board, we can actually define that in SolidWorks Flow Simulation and understand that the temperature gradient is going to be different in the plane of the board versus through the thickness. We can also define that level of physics. So you can get really specific with this stuff. Okay, so we've defined our material, which is great. We also want to define a contact resistance. So where we connect our aluminum spreader plate, where it's connected to the heat sink, we may be using a certain amount of conductive tape in that application. We want to be able to model that tape without having to actually design it in CAD. We're just going to define a boundary condition of those two parts that touch. So for here, I'm going to go ahead and just, I'm going to hide the heat sink. And now it exposes this top plate of this aluminum top plate. And I'll apply contact resistance. So since I'm using some of the capabilities in the electronics cooling module, a lot of these added materials come from the electronic cooling module, which adds in to SolidWorks Flow Simulation. So I'll go ahead and find this material in my predefined. This is it's resistance. Let me see if I can find an interface material. Kind of have to dig kind of deep here to find it. It's polypad K. So we're going to just choose one of these, a contact tape. This one, polypad K at 25 PSI. So that's going to be how much pressure is under when you actually bond that spreader plate to the aluminum or the copper part of the heatsink. Choose that surface. Cool. So now we have our contact tape. We have our materials. And the nice thing here is we don't have to set up too many more boundary conditions, or really any more, because this is an external analysis. We're going to let all of the flow of air, we're going to let that happen organically based on the temperatures that we apply to the chips and based on the fluid that's in our computational domain. So that brings us to our next task. Well, let's define our circuit chips, our LED chips. And you'll be amazed at how easy it is to define something like something as complicated as a microchip, how easy it can be. You can define all the thermal characteristics of that based on the two resistor component model. So again, this is another capability in the electronics cooling module called two resistor components. So simply by choosing the top face of my chip, it's going to select that face. It understands the body. And now it says, well, what type of chip is it? So as I go into the engineering database, there's a lot of pretty amazing stuff here. So most chips have have two really important properties called the junction to case resistance and the junction to board resistance, which is in a K per watt value. And it's usually something that the manufacturer can provide. And what that does is it takes into account all the materials that are part of that chip, all of the traces, all of the solder points, all of the complexity can really be baked into two resistance values called junction to case and junction to board. In this case, it's pretty easy for us to find the CRE ML-B information, the junction to case and the junction to board values. We create a new material, we add it, and now here we can just apply this microchip value to our part, and we'll end up doing that 11 more times. So I already have one that I've already have one of these examples I've already done, so we're not going to do this 11 more times right now. But you can see how simple it is to define a chip. Now, I didn't give it one thing I forgot to do is I forgot to give it a wattage. So we're going to say that this runs at 0.5 watts. And that's it. That's all the information that I have to add to get the thermal behavior of a microchip, or in this case, an LED chip. Okay. So we've defined all of our boundary conditions. We've defined our materials. Now the next thing with CFD is we really have to tell the solver, what are we interested in solving? See, you may be running an analysis like this, and without applying what we call goals, the solver is going to try and solve for all sorts of physics that we don't care about. It's going to try and solve for the highest Mach number. If we don't give it a goal, it's going to try and solve for things that are pretty much mean nothing for this specific model. So we need to direct the solver by creating goals. So I'm going to create some goals. So what do I mean by goals? Well, I really want to know, and I want to understand, what is the maximum temperature, in this case, maybe of each of the microchips. So I can select that microchip or the LED chip, and I want to understand what the maximum temperature of that chip is. Okay, so now I'm already starting to focus, and I'm really starting to focus the solver to say, this is what I'm interested in solving. I may want to understand some other things. Another volume goal. In this case, I may want to understand what is the maximum temperature of the heatsink and the spreader plate. So I'll choose the maximum temperature of heatsink and spreader plate. And lastly, I may want to understand, how hot does the circuit board get? Choose the circuit board and understand the maximum temperature of that circuit board. So we are ready to go. We're ready to run. It's pretty crazy how quick you can apply all of these physics, all these realistic environments to something that's pretty complicated and actually start to get a run so we can start getting some information back on our models. Okay, so I ran this one. And let's take a quick look at some of the results. So you can see in this case, I created a different chip for every one of my LEDs. I also created an individual goal for each one of my LEDs. And this, I think, takes about 15 minutes to solve on my Lenovo laptop. So not too long, but you'll be amazed with what type of information you can really get here. So let me bring back the top of my bulb. We'll make everything kind of semi-transparent. So one of the first results we may want to understand is a cut plot. So a cut plot is just a real great way to understand quickly, what does my thermal environment look like? And I can even animate this plot. Right, I've hit play. It's just going to animate from one side of my computational domain to the other. I can zoom in as far as I want. I can get really close information here. I can look at my scale to get an understanding of what the temperature is at different locations. I can also probe individual results. So if I was interested in, what is the exact temperature, at a specific LED, I can do that too. You see lots of really great understanding of the results, in this case of the airflow and the solid temperature. And like I said, we can always probe for results as well. So simply by hovering over any location of my model, you notice I'll get immediate feedback of its temperature. This chip is 87 Celsius. This one is 91. And that's just all going to be based on its environment in relation to, or its relationship to the environment and its relationship to a neighboring heat sink fin. So you get really cool results here. All right, so let's continue on. What are some of the other results that we can see? Well, we also may want to understand something like a surface plot. And this surface plot is really useful. So in this case, I simply chose the heatsink and the spreader plate, and it's going to give me an idea about the temperature of that heatsink. In this case, I have 20 heatsink fins, and we're looking at, average temperature of about 53 to 54 degrees. We can keep that plot on while we look at something like flow trajectories. And flow trajectories are going to be visually one of the most, interesting plots, but also it really gives you another dimension of results that you can interpret all at the same time. So we'll head and choose 50 arrows, and you'll see kind of what I'm talking about in just a moment. And this is where we can actually animate and view what is really taking place while we turn this lamp on. So we can watch as air is drawn in from the vents on the bottom of the LED bulb. We can watch as that air passes through the inside of the bulb and then out the top vents. We can even look at what is the temperature of the air as it comes in and leaves. So a lot of information can be gathered here. Okay. So back to our question. Did this answer the optimum number of heatsink fins? Didn't really answer that. This told us kind of how does 20 fins look? If you have 20 fins, this is what the temperature environment is. But we'd have to copy this and do a bunch of geometry changes and test a whole bunch of them to understand what changing those fins are. Well, a really cool feature in SolidWorks Flow Simulation is something called a parametric analysis. And we can actually automate the geometry change based on, in this case, one parameter, but we can do many parameters that are in the solid model. And we can use that to either optimize a model or just do a what if scenario and say, well, what if we had a bunch of different versions of this at different blades and then interpret all of those results as one package. It's really pretty cool. So let me show you how we would do that. Okay, so we have our model, which is great. Turn this off. But what if now I want to create a new parametric study. And in this case, I'm going to do a what if analysis. And that would be like, say I have a bunch of different scenarios and want to test them all at once. Like I said, we also have a goal optimization. This would be something I could do later. This would actually, I could use the goals that I've created, the goals of the different heatsink, the heatsink temperature, the different LED chip temperatures, and use that to actually direct the geometry and say, well, what's the perfect number of fins to optimize so that these LEDs are exactly 62 degrees Celsius? We can even do something like that. So that would be kind of like step 2. Step 1 would be like, hey, what if I just had a bunch of different versions of this model? So I'm going to do a what if analysis, and it's going to be based on a dimension. So this is where it's going to be searching for a dimension in my model. And so my heatsink, I have a circular pattern on my heatsink. You guys know SolidWorks, there's nothing new here. Obviously my heatsink, it goes over around 360 degrees, and I have 20 instances. Well, simply by clicking that 20, you'll notice that parameter is now in my parameter list. So I can control that parameter now. Pretty cool. So how do I want to control that parameter? Well, I can either choose a bunch of discrete values, or I can say, well, I want the range to be between say 20 fins and 100. And we'll look at intervals of 20 fins each. So it'll be 20, 40, 60, 80, 100 for now. Now, if we had a lot of time, we could have those intervals as 5 fins. It just depends on how much time you want to spend. So it's going to create those scenarios for me. Okay, well, a version of 20, 40, 60, 80, 100. Cool. Well, what about output parameters? Well, at this point, I really just want to monitor all of my goals. But if this was if I chose a goal optimization, this is where I would choose specific parameters to actually guide the geometry change, which is really, really cool. So I want to monitor all my parameters. And you'll notice now I have a scenario list. It says, okay, these are all the different parameters, these goals. These are the different designs, 20 through 100, and it's going to run all these solutions and then fill in all of where these question marks are. What are these maximum values for the LED, heat chip or heat sink, and PCB temperature? Pretty cool stuff. So obviously I've already ran this. And at about 15 minutes per, right, this takes about 150 minutes, so it's about 2.5 hours to run something like this. Sorry, half of that, an hour. There's not 10 scenarios, there's only 5 at 15 minutes, 75 minutes. Okay, so as you can see, I already ran all these scenarios. And let me just first show you all the results of them. Okay, so this is the result list after I ran that analysis. The cool thing is that we don't only need to get feedback as far as numbers go. Now you may not be able to read these numbers, but don't worry about it, because it also creates you can create a unique configuration with the study attached to it as well. And that's what I've done here. Under these design points, I have 5 design points, 1 for each. So let's look at design variation 1. You can see design variation 1 has 20 heatsink fins. As I page through the different design variations, you'll notice the number of heatsink fins will change. In this case, I have 40. Here's 60. Now, all this was done for me, which is really awesome. We have 80 and 100 fins. Okay, so let's go back to my version with 20 fins. And I'll hide this. Okay, so we have 20 fins. And maybe we're interested, firstly, in that result where I just looked at the temperature of the heat sink. So another really cool thing we can do in flow simulation is under results, I can compare results across multiple runs that are going to be in the same temperature scale. It's going to be an apples to apples comparison. The only thing that's different is the geometry and the analysis that's ran itself. So in this case, I can choose my design variations from 1 through 5, and I want this active scene to be active, and hit compare. Now this is just going to take a couple moments because it has to really collect a lot of information for this to run. Well, it actually looks like it collected pretty quick. So one very interesting result here, and it's definitely a counterintuitive result. So we basically found that more fins are not necessarily the best, right? In fact, as you get beyond 40 fins, you're really starting to restrict airflow, right? So if the viscosity of your fluid was different, well, maybe we'd get a different result. But the viscosity of air suggests, in this case, that we can see pretty clearly that 40 fins is better than 20 fins, but it's also better than 60, 80, and 100. So this is, you get kind of a 2-for-1 on this, right? You find with the coolest environment, but you also, something that at the end of the day is less expensive to manufacture, less expensive to develop, but it's also going to perform better. And those of us who've spent any time in an R&D environment, it's not uncommon to find a situation like this, that not only this is better in more than one way, it's a win-win. So this is really at the core of what simulation and simulating early in your design process can really offer you while you're designing, instead of using this only as a tool when you're already in manufacturing. So you want to use this early. So we find that, right, that 40 fins is the best scenario of all. So as we just saw, 40 fins is, in this case, the least, is the coolest of all these different configurations. So what would be the next move? Well, if it were me, I would go between 25 between 30 and 50, and then maybe go by 5s. Find that exact number of fin that is the coolest. It could be that maybe 30 is cooler than 40. We don't know that yet. So this is a first cut experiment. And then as we can even refine further, because there's no there's no negative side of having the most optimal geometry. So that may be the next thing you want to do. So obviously 40 is the best. And because the heat sink is cooler, right? That means it's the most efficiently removing heat from our system, which means obviously our LEDs in that scenario are also going to be the coolest, which means they will last longer and the performance of the bulb will be optimal. Pretty cool stuff. So SolidWorks Flow Simulation really can be used to answer very critical questions, such as discovering problems early or discovering the most optimum geometry early in the design process. And you can automate that design optimization. I didn't have to create 5 different versions and test them all at once. I just had to automate the one parameter and say, well, I want this range on this one parameter and then test all of them. And then I want to be able to post-process all of them in one batch. Pretty cool. Obviously, this is going to reduce prototyping, right? I mean, the last thing you want to do is build 10 prototypes of one part just to find out that 9 out of 10 of them perform poorly. You want to do this early. And also reducing bench testing. Now, something like this, to bench test this may not be very expensive, but sometimes certain products have to go on things like shaker tables or do something like random vibration type analysis, which is very expensive, right? So you want to, reducing testing also can save a lot of money, especially in the R&D environment. Okay, so maybe I'll open it up to some questions. I've got about a few minutes left, and if there are no questions, then we can move right on to Mike's portion. Otherwise, yeah, if anyone has any questions. No questions?
Not on that door here.
Okay, anybody here have any questions about this? Anything? Okay, cool. All right, well, thank you guys, and I'll move this right on to Mike Spence, my colleague. Hold on, just be a minute as we switch out computers.
Nobody even got the pun. Okay, cool. No? Am I the only one?
I didn't even get the pun. Okay, cool. All right. It's all yours.
I missed the instructional video on how to plug in up top here with some power. There we are. Yeah, that's the one. HDMI. Or the display port.
But that's going to go to VGA. Probably don't want that one.
Yeah, let's use that.
I'll let you do that.
Do you set a goal that would just vary the fins until one of those LED chips temperature went higher?
I'm sorry, what was that?
Could you set a design goal where you would vary the number of fins and then it would stop varying when one of those chips got?
One of the chips, well, you can have it where it reaches a
Threshold. Yeah, so
It reaches a maximum temperature that you define. Yes, absolutely. Is that kind
And
of
just let run overnight. Both do everything.
yeah, and that's called, so what I ran was a range with step. What you would run is just a range. Say 2 to 1,000 fins and just hit run and it'll just keep paging through. It uses the secant method if you're familiar with that. That's used for I remember using it in grad school, you have to use like a ruler and angles, but what it does is it helps narrow, it uses results to narrow the scope of your focus and narrows into an optimized, pretty much uses an advanced. So it'll just keep running. It'll just keep going until it hits your target value and your tolerance. So say you want.
If you didn't have a target value, you just said, I want to just find where's the coolest. Like if you had one more fin and the chip's hotter than the last time, stop.
Yes, you can set your goal to set a minimum goal. Say LED chip minimize this value based on this range, and it will find minimum.
If I understand part of your question, though, in your results, you may have a dip where you're looking for that
Yeah. Find-
vertex or the valley, right?
Throw it, yeah.
I don't know if it would
Minimum-
find
there's
the,
also minimum between two
Yeah.
extents.
Yeah, just stop when you reach that.
Yeah. And it'll just keep picking values as it'll pick values randomly and then try and determine what that shape looks like, and then try and find the minimum.
targets. Yeah.
But if there are multiple minimums, like local minima and maxima, sometimes it'll have to narrow the scope to find one minima, because it'll try and find two, and then it'll find for a long time.
Diverges instead of converging on a solution.
Yeah, it will
Yeah.
never really converge. So it's best to, like, if you know you want to be in, you want to try and understand that range best you can before you. But yeah, I had to run 40, 60 value, especially in our FEA tool, which is similar. I've had that run hundreds of different iterations before I came up with an optimal solution based on. Did that answer your question? Yeah.
All right, out of the simulation tools, same subject, we're going to switch over to finite element analysis. And again, these screens you can't see very well, so hopefully on the broadcast it's a little easier. Our choice of light gray and even lighter gray is not brilliant for some of the. This one, yeah. With the simulation tools, they're basically with the finite element tool specifically. There are several different solvers involved. I'm going to focus primarily on linear statics with parts and assemblies. But you guys do have access to all but the list on the far right, the premium list nonlinear solvers and vibration and spectrum response. But you do have all of the tools from standard and professional. So without worrying about a whole lot of detail on those, I want to kind of focus this on three of the most common things that users need to do when starting an analysis. Effective model preparation, checking to make sure it's strong enough, and then on the same concept that Andrew went through, we're going to look at how you optimize that. So model prep is probably one of the places where if you spend a little more time to begin, you can focus in on a better solution faster. It's not uncommon. It's been a little while since I've taught this material to students, but I used to. And one of the most common challenges for someone new to finite element analysis is throwing too much at it at once. And Andrew's got a good analogy. If you break out on a weekend, a slow Sunday, you break out a 1,000-piece jigsaw puzzle. You probably have a strategy, right? You probably don't just pour out the puzzle pieces and try and pick two that fit together. It's just not going to work. It might be very slow. Most of us as engineers have a more analytical way of thinking through things. So with a problem like this, it's important to hone it down on a simpler question first. This is a little piece out of a suspension system. You got the brake disc and an A-arm and a steering rod on this. And maybe if, from a race car, maybe I know I'm trying to lighten the system, number one. And number two, I need it to run so many races. Maybe I need it to last at least, 300,000 cycles for a given vibration or a given load. And based on some previous knowledge, we know that this bracket tends to be problematic. Okay, this is where we start developing cracking. You do kind of need to start or know where to start looking, right? You can do a larger scale simulation of a system, but if you're going to tackle system behavior, your geometry is going to look much simpler than what we're looking at there, right? It's not going to be your manufacturing SolidWorks parts. Even my part up here on the screen might be a little more intense than I need. So even a little more simplification comes in with choosing what to remove. Let me show you a couple things that you can do to help in that respect. And I'm going to focus on that part just for a moment. And I mean, just for kicks. Well, take a look at this part. What might you do to simplify this part for finite element analysis? Essentially what we're doing is we're asking what is not going to impact the structure of this part. Yeah. Small rounds, right? Luckily, those are applied as a feature, so we'll just suppress those. And even before I do, you guys are SolidWorks users, you're probably going to want to separate your manufacturing part from your analysis part in one way or another. Now, brute force way, you could certainly pack and go the whole thing and have a whole separate assembly if you really want to keep your data separate. But configurations are a great way to go as well. I know a lot of users who will regularly use configurations, whether it be an FEA configuration or a simulation configuration. And if you use a common naming convention, if you're sharing any models, then you kind of all are speaking the same language. Not a bad idea. Okay. Sometimes this becomes a little more challenging if this was not a model that you created. Maybe you imported it from somewhere else. So just as a little tip, if you didn't know this, if I needed to get rid of all of that embossed text, because that's going to be painful for the mesher, and it's going to make the mesh more detailed than I really want it to be for a quick simulation. It's not affecting the structural integrity, at least I don't think. You wouldn't know for sure unless you actually ran the simulation with both to find out the difference. But if you're not familiar with the direct editing tab, give the delete face tool a try. That is like the universal Bondo tool for SolidWorks. It's pretty awesome. Turn on the tool first, and if I pick the bottom face of one of those cutouts, the quick selection bar comes up to help me out with some selections. It'll either select all of the surrounding faces for me, all of the outer faces, outer and inner loops, which are the same connected faces, all coplanar faces. So you can see how it's running the base of some of the other text. Well, all coplanar and connected faces. Pretty slick with text. Okay, that grabbed a whole lot of the selections, but it happened to miss the D. Okay, well, I can make one more selection, and I'm going to hit the same option. And on the delete face tool, if you're not familiar with this one, delete and patch. It's pretty awesome. If you're looking for more like the Bondo and sand, that's delete and fill. So if you want to try that out, it's pretty cool. This isn't all about this tool, but man, that can be extremely helpful. It actually adds a feature to the model. So you suppress that feature or roll back, and obviously your text is back. So if you've imported something with features that you want to get rid of, you don't have to extrude over the top. Try the delete face tool. It does a great job. Okay, so I might have a simplified configuration of the part. Now, I would recommend starting as small as possible. So when we look at the strength, I'm going to start with the part, but in simplifying the model, I might also, actually, I think I put this slide a little out of order. I did. That's all right. Well, even though we're not talking about strength yet. Analyzing the part itself might give me some behavior of the part. Well, let's come back to it when I get to that. Let's go into the strength. I don't want to jump the gun here. Let's start just from the basic part. Now, certainly you can jump in and use the Evaluate tab and grab the Simulation Express Analysis Wizard, and that'd give us a decent simulation on this part without having to do a whole lot else. But you do have access to the simulation tools, so I'm going to just pop one in and just do something pretty rough, but it'll at least give me a general idea of behavior of the part. This is going to be bolted to a component behind that is really rigid compared to this component. So you basically just go down through the tree. It'll automatically take the material properties of the materials that you've signed in SolidWorks. So if you're doing that carefully, then you don't have to do anything additional here. Connections, you can replace or represent things like pins and bolts and springs on the model without having to have them modeled. Saves you a lot of performance. Fixtures are how it's attached to the world around it. So I'm just going to do something pretty rough in this case. I'm going to just say, hey, these cylinders where I have bolts, I'm just going to assume they're fixed. Those areas will not move at all. And I want some load applied. About 3,000 pounds is the highest load I see on this steering rod. So I'm going to add a force based on a couple faces. Now, you can specify direction here, and that'll help me out. You can either use linear edges, planes, model faces, whatever it happens to be. Set the units appropriately, but the biggest thing to watch out for when you're doing this, especially if you're selecting multiple items, is whether you're assigning the load per item or total. I have 3,000 total pounds, so make sure you select the right option there, or you'll get some wonky results. So let's see. Yes. So if I knew it was 1,000 pounds per face, then I'd pick per item, pick the faces, and apply 1,000 pounds, and it would be, if I had 3 faces, it would be a total of 3,000 pounds. Yep. All right. And I've seen this occasionally, and I don't know if it just plagues me or some others, but sometimes entering values there don't seem to be as consistent as entering them on the little flyout call out. 3,000 pounds. Make sure the direction is correct. You can reverse that direction just like you would with other SolidWorks tools there. So that's kind of quick and dirty. In fact, even at this level, I wouldn't even worry about what the mesh is. I can just right click on the study and run it. You're going to get some quick results. Okay. Now, one of the things I'd recommend doing right away is animate the results to see if you're seeing anything that looks out of place. A couple things happening here that probably wouldn't happen with the rest of the assembly in place. The 2 flanges are separating. Well, I might have something holding those so they can't separate, whether it be clips or pins or bolts or whatever it happens to be. The back end also is deflecting inward towards what I have is basically a rigid body behind it. So, okay, that may not be the greatest representation of what's going on. So can you improve that? Yeah, with a few different restraint types, you can improve that to maybe be a little closer to what's really going on without having to put the entire assembly together. So in your fixtures, there are a few other types that are pretty straightforward and also represented well with some little quick images. Like a roller slider restraint will prevent something from moving out of plane. Fixed hinge will allow something to only rotate. But in this case, a couple of roller slider restraints could help me out significantly. All right? So if I just say, well, I'm just going to say, hey, that back face, I'm going to put a roller slider restraint there. And on these 2 cylindrical faces, or sorry, flat faces there, little discs, those will now not be able to move out of plane. So what kind of results do I get? Now I get much more of the flex that I would expect without a lot of that additional distortion. Now, one thing about that too is it does not allow that part to flex away from the rigid body either. Okay? A roller slider restraint means it's going to hold in plane. That may be fine. It may not be as accurate, and you're going to have to make that judgment call, right? Okay. But now I'm getting more of the deflection that I would expect. Now we are still getting some cylindrical distortion here that may not really happen because I have a pin through the hole. Not only that, but that force is also pulling on the back of that cylinder, which unless we're welding it together isn't really going to happen. But this is starting to give me a good idea of what's going on. Now, compared to the yield strength of the material, I've actually already exceeded yield. Anytime you see this little red marker on the color plot, you're exceeding the yield of that material. So if I'm already exceeding yield, well, this is going to be horrible in fatigue. Okay, so maybe I decide, well, let's go for a material that's a little stronger. Right now, this is just using a basic galvanized steel. Let's go for a good, like 4130 alloy. Okay, and just like with thermal analysis, the great thing is you can make an adjustment, rerun the study, and test again very quickly. And now we're, roughly, well, a little over half, 2/3 of yield on the material. Okay, well, I like the basic idea, but maybe I really want to understand what's happening with contact stresses around this part of the component. So let's see where we can go with this a little further. Right? So starting small in terms of simulation, then add on a little more geometry. You don't have to throw a ton of geometry at it. But here I can get kind of the pin behavior to add a little more detail. Now, in the real model, I also had a threaded rod coming into this spherical ball end. I may not need that. The great thing about threads is they're designed to be able to handle a given load with given thread engagement. Use a spreadsheet for that, basically. Unless you're designing threads. Well, then you might want to do some 2D analysis of the threads themselves so you can get a very detailed mesh for accuracy. Right now, though, I haven't even bothered looking at my mesh. At first, I may not even care about how academic is this solution. I want to know relative merit, right? If I'm designing, I want to know, well, is this design better than this? Which tends to distribute the load better and give me better stress distribution? Then at some point, I may want to start to refine and say, I like this. Let's see how accurate my solution is. One of the hardest things to do is actually take something that did fail and mimic that 100% in analysis, right? I mean, that's gets down to extreme academic level there, and really being careful about the way every part interacts with each other. It's one of the most difficult things to do. Easiest thing is to compare, get relative merit, know, the design I have is better than these 4 others. And give us some other design insight into what we might do to improve it. So let's hop over to the assembly again. And I've already spent a little bit of time simplifying this assembly as well. All right, so we got rid of some of those threads. We don't need that really. In fact, I don't have this whole spherical ball end. I just have part of it because I've got it lined up for my load direction. Okay. So I've already kind of run through the setup, so let's take a look at a few other details. In assemblies, connections are even more critical because connections include not only things like replacing bolts for a bolt connector, which gives you the behavior of the bolt, even preload of pre-tension on bolts, preload, pre-stress. But it can also define how the parts interact with one another. So by default, when you put an assembly together in SolidWorks and then run a simulation, all the exact touching faces will be treated as bonded, as if they're welded or glued together. But in this case, that's not really the behavior I want. Between the spherical ball end and the sphere itself, I want to be able to see some separation. If it's pressing on that sphere, I want to be able to see that ball end separate on one side and get the contact stress on the other. So you can go through and select contact sets. So basically in the connections area here, let me zoom in on that for a moment as well. In the connections area, you can add contact sets. In fact, for component contact, it'll find all the parts that are touching, and then you can define what each of those touching surfaces does. In this case, I found this contact set between the sphere and the spherical ball end, 2 touching faces, and I've given them a condition of no penetration. There are a few different options available there. No penetration means they will not go through each other, but they can separate. It's a heavier calculation than bonded, so you are getting a trade-off here. It's going to take a little more calculation time, but you get a little more realistic behavior. allow penetration might be for something you don't care if they actually overlap. And if you see it, then you might say, oh, okay, well, I need to change the way I'm doing the simulation. That's really low cost on the calculation. A shrink fit is if you have intentional interference between the parts and you want to see the result of where the geometry comes to a neutral position between the two. Okay, but I've got a no penetration contact here. It may be interesting to see that up at this interface here or even at the interface of the pin. But I'm going to assume I've got maybe a press fit and I'm not as concerned about those separating as I am about this, just as an example. So that's part of it. And you'd asked, I apologize for forgetting your name. It was Jeremy. Yeah. You'd asked a little bit about what makes an assembly analysis different than a part. And it's largely those contacts between the components that can make a big difference. Obviously the materials, right? Because we have an assembly, each body in the assembly or each body in a multi-body part can have different material settings. And in fact, to simulation, it really doesn't, for all intents and purposes, it really doesn't know whether it's an assembly or a multi-body part. Shouldn't care. You were mentioning you were running into some things and we can maybe offer some ideas a little bit after, but it shouldn't matter between the two. Everything that I haven't explicitly set in a contact set will just act as bonded. So I have a global condition that anything else touching just going to be bonded together. I've done the setup just a little bit different on the holes. Instead of fixing them, I've added a fixed hinge. So those will allow some rotation, but no axial movement. Got a roller slider restrained on the back face again, kind of representing a rigid surface behind. And to prevent, because this has a no penetration contact condition, it could fall, move, rotate. There's no friction on that. I don't think I have friction on that. You can't put friction on a contact set, but there isn't any. And so that thing could move anywhere. If I tried to solve that, the solver would fail because it just had too many solutions it could go to. So I've restrained that movement by choosing the option on cylindrical face. Okay, if you pick a cylinder, you'll have in the advanced settings, because I have a cylindrical face selected, I have all kinds of options, and on cylindrical face helps me very easily set, do I want to allow radial expansion, rotation, circumferential rotation, or axial movement? And I can restrain whichever of those directions I want, or prescribe a displacement. If I want to force an axial displacement of 1 millimeter rather than adding a load, I could choose that option. So essentially put us in a cylindrical coordinate system. And in this case, I was able to apply that force directly onto, there we go. I was able to apply that force directly onto this face. I didn't have to divide it up because that load will be carried through those components. All right, so running the entire assembly, let's take a look at this. And in fact, I'm going to modify the scale so it's an exaggerated scale. When you saw that part deflecting in the other example, it was an exaggerated scale. I probably should have pointed that out. But with the exaggerated scale, I can also see there is some separation between the spherical ball end and the ball itself. And based on the stresses you see as well, you see that contact stress building on the left side where you don't have that contact stress on the right. And I don't remember what the number was that we were looking at on the other part, but I do believe in this case, with this setup, with this, with the additional parts, the stress is a little bit higher than the maximum stress that we were seeing in the other component. It's pretty close. It's in the similar location. So if I were going to then start optimizing this, if I was getting similar results at this point, I might decide, okay, well, if I'm optimizing, I'm just going to do it on the part, because then I can iterate through solutions faster. If I was getting a drastically different behavior here, then I might want to do my optimization in the context of the other components. Now, this is kind of a cool problem because it needs to last. Needs to have a given amount of durability. Okay, so we're well under. I think the yield stress for tensile yield of this 4130 is about 560 megapascals, and we're sitting at about 276. So roughly half. But where is that on its fatigue curve, on its SN curve? So I've run a fatigue study on this same problem. To set up a fatigue study, you just point it to another simulation, a static simulation, and say how many events of that type are happening. You can even add multiple simulations. So if you have an event coming in from the top and a side load and another directional load, you can say, well, I'm getting 10,000 of these and 100,000 of these, and I want to try and get 1 million of these into the simulation. But running this, my life plot basically gives me how many cycles could it withstand, and we're down around the 180,000 cycles before we're going to start introducing fatigue. And the fatigue estimates are not conservative because of surface finish and corrosive environments. That could drop this significantly. So it may give us an idea of saying, well, okay, if this is ideally in a perfect geometry, we're looking at 180,000 cycles, I might decide to start checking this for cracks at 100,000. But it's still not lasting as long as I want it to. So what could we do to get to optimize this problem and to get better behavior? And this one's kind of fun because it gave some kind of counterintuitive results. Let's just focus on just if we were going to optimize this part for mass. Right now we've got this geometry, right? And we're focusing on the bracket. You can't change the spherical ball end. Well, what would you change on it? And I am looking for some feedback. What would you do to reduce the weight of that bracket? Any thoughts? Got some holes in it? Where would you cut it? Like the little wings that come out, the tabs that come out, or the back, or where would you cut the holes?
The back in the middle.
Maybe the back in the middle?
Yes. Yeah.
Thickness?
Locally where you need it, and then thin it out where you don't need it.
Okay. That's an interesting comment. Thin it where you need it, or sorry, keep it thick where you need it, but thin it where you don't need it. So how many of you look at this and know where those places are just by looking at the part? Maybe the more experience you have, the more you tend to see, okay, I'm used to what happens here, and this is where the load's being carried. But if you don't, one of the best plots I think that SolidWorks Simulation provides is called a design insight plot. This is pretty slick. So our stress plots kind of give us an idea, right? Areas of lower stress. Well, in theory, they're lower stress, so they carry lower loads. But if you right-click on the results folder, there is another folder called, stress plot called, and in fact, it's just right up. They put it right up on the toolbar to try and make it a little more easy to find and more accessible. It's called the design insight plot. So from an existing static study, fire up a design insight plot, and it gives you a description, but the idea is increase the slider until you see continuous mesh elements, essentially, connecting everything you need connected from the load to the places where the load is restrained. And that should give you a basic idea of where the load's being carried through the design. Okay? Obviously through the cylinder and then back here, and look at the back. Well, let's increase that just a little more. You kind of start connecting up that back end. Notice we've got a big gap in that. That's really not doing much of anything for us for load carrying. Now, it may have some other design criteria, right? That may help us fit it into place, or it just maybe just simple to manufacture. But that would be a great place to start removing some mass. Now, is that going to stiffen the part, or is it going to make it more flexible? If it is more flexible, is it going to get us too much deflection and too much displacement? So then it feels weak. Is that going to be okay? So if we do that, we do need to still make some design decisions and probably do some more simulation. So I've made another configuration in this model, and your analysis setup or your simulations can be related to a configuration. So when it shows up all grayed out, it's because it's an inactive configuration. I can right click on that study and activate that SolidWorks configuration. And you can see what I've done here. And actually, I shouldn't say I have, because Andrew came up with this good idea. Just cut a slot in the back. Okay, so what do the stresses look like? Stresses are actually lower, which is pretty cool. We get a little more flexibility in the model, and since it's not so stiff, it gets better distribution of the strain energy through the part. Yeah.
Was your load in only one direction, or was it a fully reversing load?
Fully reversing for the fatigue study. Yeah, I didn't actually show you the total setup there, but great question. Okay, we still have the same kind of stress hotspots in the same place, but who would think? When you remove some material, make it a little more flexible, get the stress distribution or strain distribution move through the model, the stresses actually go down. So our fatigue life ends up being over 1 million cycles, 1.3 million cycles. So now we're starting to actually get over-designed by removing a little bit more of the material. So where's the balance point, right? I mean, these certainly help us. These are guiding us in a direction to help get a better design. So let me introduce the same kind of optimization idea here, but instead of giving it finite values, because this isn't a sheet metal part, we're not limited to gauges. We can cut those slots as big or as small as we want. It's a machined part or a cast part. I can make this radius as big or as small as I want. I can make this wall thickness as thin or as, well, hopefully not thicker than this. And then hopefully end up with the lightest part with the best stress. Now, to keep our stresses under the fatigue limit, I want to keep them under, let's see, if we go back to our stress simulation here, we're getting up close to 220 megapascals. I don't need to run this thing a million cycles. So let's say 230 is our stress limit that will keep our fatigue limit high enough that we can run it enough cycles. So I can go higher with the stress. So what you end up doing is in the simulations, you create a new study in the simulation tool set, and you perform a design study. Now you can take this either as a true optimization, or like Andrew was showing with the number of fins, you can do more of a design of experiments where you set up a bunch of variations and let it run all the variations. Do it either way. Okay, so we'll do a design study, and let's call this, yeah, that's great, design study 2. By default, it assumes it's going to run an optimization. You don't have to. If you're just doing a design of experiments, just see behavior over a variety of shapes, you can turn that off, and it'll just run all your scenarios, and then you can iterate through them and see how they look. But we need some variables. In this case, like Andrew's, it was a model dimension. These are parameters. So let me back out here a little bit. And let's go with the thickness of the plate. I've already got that as one of my model parameters here. Actually, let's get that slot in there. Okay, so double click on your CAD geometry to show the SolidWorks dimensions, right? And let's go here and call this slot width. Apply that one, and when I apply it, it adds it to my variables to change. Let's also add this slot length. Let's see. make sure I keep that one attached to this. There we go. And the new one for the slot length. Slot length, and apply that one. Oh, we'll get them in there. And maybe I want to do, well, let's just stick with those two, just for something that's reasonable to run. But I could add in the radius dimension here, anything else I wanted to. Make sure that's slot length, yep. Okay, once I create those parameters, they're available down below to select. Now, as was discussed a little bit, you could do a range with a given step. Great if it's sheet metal or a purchase part where you have discrete values. But I just want a range. And for the slot width, well, it's 20 right now, so let's go between 20 and, I don't know, maybe it's a good idea to check your model, see, how wide can you make that before it starts cutting into other features. I didn't check that, so let's go like 27. Make an assumption. The slot length, right now I think that was, it was 28. Let's try and go from, I don't know, I don't assume it would get lighter at a lower value, but let's try 25 to 30. Make sure that one's a range as well. I'll double check those. Constraints. You guys familiar with sensors in SolidWorks? Not used very often unless you do optimization studies. Or if you want to have some design flag that if it hits a given value or above or below, you get a warning in the feature manager. Okay. I already have a couple in the system, performance stress and the mass. But let me just show you quickly where you add those. It's in the SolidWorks feature tree under the assembly here under sensors. So it's in any part or assembly. Okay, if I add a sensor here, what is it? Is it simulation data? For example, if you're trying to monitor stress, well, that's simulation data. If you're trying to reduce mass, your mass is going to be a trigger there. Could be dimensions. Some customers will, model a hole next to the edge of a part, put a dimension there and say, okay, don't let that dimension get any smaller than this value or trigger a warning or an error. Or measurement, that'd be a better way to do that because then you wouldn't have a dimension there. So there are quite a few different things you can set for sensor data. In fact, if I choose simulation, you can see where you can grab any stress characteristic, displacement, frequency, thermal characteristics, acceleration, factor of safety, a lot of data that you can get to. I already have these created just so we can do those quickly. Let's do stress is going to be my constraint, and I want to keep it less than, what did I say, 230 megapascals, right? And in doing that, you also choose which simulation it's based on. As we're dealing with a given configuration, there's only one stress analysis related to that configuration. So that's the one I want it related to. But then if I wanted to also include natural frequency characteristics, I could include that. Even if it's another study, I can optimize on both. And for a goal, well, almost always it's minimize the mass. So I've got a mass sensor in there, and I'm going to leave that on minimize. And as long as optimization is turned on, I can just let that run, and it will crank through the simulation, iterating through different values. Typically starts at the top end, then the bottom end of your values, and then starts doing some variations. And as Andrew mentioned, there's a statistical method it uses to hone in on the optimal result. So it already knows it's going to do that in 11 studies, as long as it has enough targets, and that's based on the number of variables you give it.
So if you put in another study like the frequency, you would have to run both studies?
It does. Mm-hmm.
Okay, so it would be 22 studies.
Well, it still gives the same number of iterations, but behind the scenes, each time it does an iteration, it runs all studies associated with that iteration. Okay. So here's a place where having the model optimized makes a big difference, right? I mean, you could probably looked at this model and said, well, is it really going to make that big of a difference if we turn off the fillets and turn off that SolidWorks text? For all intents and purposes, at least for my own personal feeling, it wouldn't really make a difference. But then I started to iterate, and each one was taking an extra 30 seconds. I might get really frustrated. And I might not be tolerant enough to wait for that. So I might want to put in 10 minutes of SolidWorks modeling up front so that I don't have to wait another 2 hours on the back end, just for machine calculation. It actually will color code these iterations. I should have given it a little more broad range. It'll color code the iterations to tell you failing iterations. Any iteration that goes beyond your limit, right, your constraint, will highlight in pink. So this one wasn't that exciting. So the optimal are the high end of the values that I gave it. Okay. Should have given it a little more headroom. That's great. I know that now this geometry, it finishes on the optimal, okay? But if you want to see the results from any of the others, you can show the stress plot. And then if you look at another iteration, it basically keeps the parameters in the background. It rebuilds the geometry with those parameters and then shows you that graphic, okay? So for each of these iterations, I can see how the stress distribution ended up. And if I click on optimal, it sets those dimensions at that value, and I'm ready to move forward. Okay? So that's a great way to let it target in on the optimal geometry for you. Now, we do have some exciting things coming that I can't really tell you much detail about, but with our 2018 release, it's in beta right now. And I'll just say it this way. With optimization like this, we're limited by parameter characteristics, right? You have to have a dimension there. You can't say, well, if it could use a hole somewhere, open up a hole. You can't really tell it that, right? You give it the dimensions, and if you imported a model, well, there are no parameters for it to change. So you'd first have to apply some maybe direct editing or some feature works to it so you had editable features for it to attack and optimize for you. But by doing that, we're able to come up with something that's even better. And I think in this case, just from the first shape that I showed you to the one that we finished out on, it's about a 10% reduction in mass on that part, which if you're dealing with a race car, that's pretty good. And even better, a 7 times longer fatigue life than the initial design. And, you know, in some respects, you wouldn't necessarily know that it would help your fatigue life by cutting out the back end of this unless you tried it out and simulated it. Kind of, I guess, as a wrap up for both of our presentations, kind of where do you go from here? What do you do with this now? You already have access to the tools. Is there any special process for them getting access to these, Lars, or is it just
on the SNL? The
okay?
only thing I couldn't say is you guys said we had plastics, and I don't see it on our SNL.
Okay.
Bruce Perkins, I thought he said that. I thought there was an email that he said that you guys do have plastics. I'll research that.
Okay, you let me know, because I already have something. That's the only question I got so far. Is how do you get plastics loaded? Because the rest of them are in a pull-down. You can grab any of them.
Perfect. Perfect. And these are a little more specific to my topic, but there are great tutorials on most of these topics. The flow simulation tool, the static simulation tool, each one of the different solvers. Just hop into the help menu in SolidWorks and go down to the tutorials. And there are detailed tutorials on every single one. We have quite a bit of simulation training available on My SolidWorks. So if you haven't been there, this is a portal that we put together years ago to kind of give you a one-stop shop for our knowledge base, online video content, the discussion forums, as well as some formal training material that's been produced. There's a bunch of free training that's included with typical subscription, but there are also inexpensive annual training options where you can get thousands of different training courses. Maybe thousands is an exaggeration. Do you know the number, Andrew, by any chance? There's a lot of data there. And they keep coming up with new courses left and right.
I mean, last time I looked, it was like everything in parentheses for different topics.
Yeah.
And there, I mean, it could be thousands, and yeah, definitely hundreds.
Yeah. A lot of online training. And of course, Lars can connect you with all kinds of additional training as well. But, you know, if nothing else, make sure you use it. Use flow simulation. Give that a try. Use the SolidWorks simulation tools. And you have recommended procedure if they run into questions or problems that they have. What's the Google X official procedure for getting help if they run into something?
That's a fine question. We don't have like a particular one Google-wide. Certainly here at X, the team that I work with, X Central Services, help you out if you guys need simulation. We're getting started at least.
Okay, excellent. Other questions from the group online or from?
No, looks like we're good.
Okay.
Thanks very much for coming.
Absolutely.
I just wanted to close it down, let you guys know that this coming Monday, there's going to be another SolidWorks seminar on troubleshooting. So things like external references, clearing out all those red and yellow dots out of your feature manager tree, things like that, that we get a lot of questions on. Next month, we have one of the hands-on SolidWorks fundamental classes, as well as a class that Hawkridge is going to come in and do on the SolidWorks electrical package. So that'll all be coming up next month. Thanks everybody for coming. We'll send out a survey at the end of this. That's it. Perfect.